Hello, you're listening to the Science of Everything podcast, episode 23, Chemical Reactions, and I'm your host, James Fodor. In today's episode, we're going to have a look at chemical reactions, how they're represented in the form of chemical equations. We'll give some examples, and then I'll talk about various aspects of how chemical reactions work and why they happen, including such topics as thermochemistry, collision theory, reversible reactions, and I'll also go through some of the different types of chemical reactions. Chemical reactions is obviously a very large topic that occupies a substantial portion of chemistry, so this is only really an introduction today. Also, I recommend that you have some background in basic chemistry topics like atoms and molecules, compounds, chemical bonding, that sort of thing. Episode 9, Matter and Molecules, and episode 15, Chemical Bonding, would be useful prerequisites for that sort of thing. Okay, so let's get into it. Okay, first of all, what is a chemical reaction? Chemical reactions, also called chemical change, is a process by which one or more pure substances are converted into one or more different pure substances. A pure substance is basically an element or a compound, so it could be hydrogen gas, it could be water, it could be sodium chloride, whatever. So whether it's covalent or ionic or a single element or a giant molecular compound like diamond, whatever, as long as it's a pure substance, it has a specific chemical formula that you can apply to it and given properties, then it's a pure substance. If you have one or more pure substances and then something happens, there's some kind of process that goes on, and they're converted into one or more different pure substances, we call that a chemical reaction. So when water evaporates or when water freezes, or when something gets heated up to a high temperature, when a rock gets broken up into small pieces, none of those are chemical reactions or chemical changes, because the substance of which the rock or the water is made up has not changed. It was water in the first place when it was in liquid form. Now that it's been heated, it's still liquid. If it's heated even further and the water molecules pull apart from each other and become gaseous, it's still water because the water molecules themselves haven't changed. Their relationship to each other has changed, so the water has changed state, but the pure substance, namely water, is the same. Therefore, there has been no chemical change. Same thing if you freeze water. In the case of the rock, there hasn't even been a change of state in this case. If you just break it up into smaller pieces, there's been a physical change. The lattice structure has been disrupted and broken apart, but the ionic compound or whatever else, or metals or whatever else is in the rock, is still the same. A rock also isn't really a pure substance, but even if you did have a rock composed of a single mineral and you broke it up into pieces, it still wouldn't be a chemical change because the fundamental compounds or elements or chemical structure of the thing is still the same. So basically, in a chemical reaction, atoms are rearranged and regrouped through the breaking and making of chemical bonds. So in order for a chemical reaction to occur, we have to break and then make new chemical bonds. So in the water molecule example, if we just pull the water molecules apart and make them so that they're gaseous, or we put them together in a tighter structure so that they're now solid in an ice crystal, we haven't broken any bonds, at least not molecular bonds. So we have broken molecular bonds, but we haven't broken atomic bonds within the molecules. In order for a chemical reaction to occur, we'd have to split up the hydrogen and oxygen atoms within the water molecules, pull them apart or add some other atom in there or something like that, in order to form new bonds and thereby forming a new pure substance. So that's the fundamental idea of what's happening to a chemical reaction. You're making a new fundamental substance by making and breaking chemical bonds between atoms. The other thing about chemical reactions is that in a purely chemical process, you cannot create atoms or destroy atoms. The number of atoms and the types of those atoms have to remain the same. Now, you can change the type of atom in a nuclear reaction, but they're not a chemical reaction, it's a different type of process. In a purely chemical reaction, say if you start off with 3 carbon atoms, 4 hydrogens and 2 oxygens, you have to end up with 3 carbons, 4 hydrogens and 2 oxygens. They may be arranged differently and combined into different arrangements or different compounds or whatever, but they have to all be there. You can't change the form of the atom or remove it completely. That's basically the law of the conservation of matter. Now remember, that only applies to chemical reactions. In a later podcast, we'll look at nuclear reactions where you can change the atom, but that requires a different process. If you're going to change what the atom is, you can't do that by simply rearranging atomic bonds, which is what happens in a chemical reaction. It's really just a definitional thing. By defining a chemical reaction as purely a process involving breaking and remaking bonds between atoms, we exclude anything that involves actual changes within the atom itself. It is a bit more fundamental than just definitional things, because chemical reactions basically exclusively involve the electromagnetic force, the attractive forces between electrons and the protons within an atom and also between different atoms. Whereas when you get into nuclear reactions, it involves the strong and weak nuclear forces, which are completely separate things, but we'll look at those in another podcast. So, enough on definitions. Chemical reactions are represented in a particular way, namely chemical equations, and you've probably seen these before. It's basically a bunch of letters and numbers. The letters in chemical equations are the representations of the elements involved in the reaction. So most of the elements on the periodic table, 120 or so, each of them is represented by between 1 and 3 letters. So many of the simpler elements are represented by a single letter. For example, oxygen is represented by an O, carbon by a C, hydrogen by H, and so on. Many elements require 2 letters to represent them because obviously there are more elements than there are letters in the English alphabet. So aluminium, for example, is Al, chlorine is Cl, and so on. Anyway, so when you see a chemical reaction, you'll see all these letters, and that's what each of them refers to, a different element. Another important feature of a chemical equation is you'll see an arrow in it somewhere. Or it could be a double arrow pointing forwards and backwards, but there'll at least be one forwards arrow. The things on the left-hand side of the forwards arrow are called reactants. The things on the right-hand side are called products. Basically, the reactants are the things you start with. The arrow means like produces or yields or goes to, however you want to interpret that. And the reactants on the right-hand side are the things you end up with. So remember, we said the chemical reaction is just a rearrangement and regrouping of atoms by breaking and then remaking chemical bonds. Well, the atoms that you start with, atoms and compounds that you start with, are on the left-hand side. They're the reactants. The things you end up with after shifting around those bonds and atoms are on the right-hand side are called the products, and they're always separated by that arrow. Now, in chemical reactions, we also often represent the state that the reactants and products are in by a little subscript in brackets. So the main ones use the G, L, S, and AQ. So G for gaseous, S for solid, L for liquid, and AQ stands for aqueous, which means dissolved in water. So for example, if you mix salt into a glass of water, if you were talking about the H2O itself in that water, that would be liquid, but the salt, the sodium chloride dissolved in it, would be aqueous, which is the free ions dissociate and dissolve in water. We'll talk more about how that works in another podcast, but just be aware that it's not so much a different state of matter, it's just an important, because water comes up so often in chemical reactions, we have a sort of a separate category for things that are dissolved in water, and we call that aqueous. The other main component of these chemical equations are the numbers. There are 2 places you'll see numbers in chemical equations. So one of them you'll see little subscript numbers, 2 or 4 or 6 or 12 or whatever, to the lower right hand side of the atomic symbols. And you'll also see larger numbers out the front of of symbols. So for example, H2O, you've got a H which stands for hydrogen, an O which stands for oxygen, and then say that was in the liquid state, then you'd have an L, a subscript L for the whole thing. But there's also that 2, which is where the 2 in H2O comes from, which is a subscript 2 to the bottom right-hand side of the H. And that 2 means that there are 2 hydrogens bonded to every 1 oxygen, forming a H2O or water molecule. But you can also have a 2 or 3 or any number you like in front of the H2O, which means that number of water molecules. So for example, if you have 2 H2O, that means you've got 2 water molecules, each water molecule which is in turn comprised of 2 hydrogens and 1 oxygen atom. So if you have 2 H2O, that means in total you've got 4 hydrogen atoms and 2 oxygen atoms. So if you had 2 H2O on one side of an equation, say in the reactants, you'd have to have 4 hydrogen atoms and 2 oxygen atoms on the other side, in the products side of the equation. Now, they don't have to be in water molecules, and they don't have to be in that same relationship, but they still have to have that same number of atoms. Remember, that's the conservation of matter. And so a large part of what you do in chemistry, I guess in particular earlier courses, is balancing chemical reactions. Because you might know that this chemical compound with this ratio of, say, carbon and hydrogen or whatever elements reacts with something else to produce this other chemical compound with this different relationship or ratio of elements. And they're the same elements, so you've got carbons and hydrogen on each side, but the compounds have different ratios of elements, and so you have to combine them. You have to combine the molecules of those 2 compounds in ratios that allow you to balance out the whole equation. So let me just give you a few basic examples so that you can get some sort of idea. So for example, if we have aluminium and oxygen reacting to produce aluminium oxide, which is basically like aluminium rust, we'll have an ALS, which means 1 solid atom of aluminium, plus O2G, which means an oxygen molecule in the gaseous state. It's O2 because an oxygen molecule is comprised of two oxygen atoms bonded together to form a single molecule. Then you will have an arrow, so that produces aluminium oxide. And aluminium oxide, in turn, is a molecule with a ratio of 2 aluminium atoms to every 3 oxygen atoms. So that will be Al2O3, and that whole thing is in the solid state, so that will have an S. Now that reaction that I've just given you there is not balanced because we have 2 aluminium atoms in the products and 3 oxygen atoms in the products, but only 1 aluminium atom in the reactants and 2 oxygen atoms in the reactants. So it's not balanced. We have a different number of aluminium, different number of oxygens on each side of the equation. So we'll have to play around with the numbers of atoms or molecules on each side of the arrow in order to get the thing to balance. So for example, we could put a 2 in front of the aluminium, so we've got now 2 aluminium atoms reacting with every 1 oxygen molecule. That would get the 2 aluminiums that we need, but then we still have to fix the problem of the 3 oxygens that we need to form the aluminium oxide. So we could put a 3 in front of the oxygen molecule, but then we've got 6 oxygen atoms because each oxygen molecule is composed of 2 oxygen atoms, and that doesn't work because we've only got 3 oxygen atoms in the product side of the equation. So, I won't go through that example in complete detail, but you can see it's a matter of fiddling around with the numbers to make sure the equation works and everything is balanced. Another example of chemical reaction would be methane plus oxygen produces carbon dioxide plus water. So this is basically burning natural gas to produce energy, and it gives off water and carbon dioxide as byproducts. Now, all of these will be in the gaseous state under normal conditions. Methane, the chemical formula for that is CH4, which means 1 carbon bonded to 4 hydrogen atoms, plus O2, so that's your oxygen molecule again, produces CO2, carbon dioxide, 1 carbon atom for every 2 oxygen atoms, and H2O, which is water again. But if you just had that form, the equation won't be balanced. And so once again, maybe you could write that example down and work out how you would balance that so you have the right number of atoms on each side of the equation. Okay, so that's the basic idea of a chemical reaction and how they're represented in chemical equations. You can write a chemical equation in words as well. It doesn't have to be using those symbols. It's just commonly written using those symbols, the chemical symbols and the numbers, for convenience sake. Now we're going to move on to the topic of stoichiometry, which is sort of a scary sounding word, but it just is a branch of chemistry which deals with measuring the relative quantities of reactants and products in chemical reactions. And so relative quantities is a bit of a interesting concept because there's different ways you can measure quantities. In particular, the main things that are often of interest in stoichiometry are the number of atoms or molecules on each side of the equation, or you can talk about the mass of the products and the reactants, or the mass of particular elements or compounds that are reacting. So that's measuring it in grams or kilograms or whatever. Or we can talk about volume, which is particularly common for things involving liquids or gases or aqueous solutions. Okay, so why is this in any way interesting? It's interesting because of the way that these things can be worked out. So for example, if you know the ratio of, say that you have A plus B produces some other compound C, and if you know the relative numbers in terms of amounts of molecules of A that react with B and the numbers of C that they produce, and if you also know the molecular mass or atomic mass of A, B, and C, so of the mass of a single molecule of those things, then you can just multiply that out and work out what the mass of the products will be and what the mass of the reactants will be. And then you can weigh what you actually get and compare it and see if you've done something wrong or not. So a key concept here is that of the mole. And we're not talking about the furry creature here, we're talking, it's spelled M-O-L-E, but it's a unit of measurement which is used in chemistry. It refers to an amount of substance. Basically, it's defined such that 1 mole is an amount of substance that contains as many elementary entities, they could be atoms, molecules, ions, or electrons, as there are atoms in 12 grams of pure carbon-12. That's a complicated definition. It's also equal to Avogadro's constant, which is 6.022 by 10 to the 23, so that's 10 to the power of 23, so that's a very big number. But what am I saying here? All I'm saying is that a mole is a really big number that refers to the actual physical number of atoms, molecules, or particles that are in a given substance that you're given. It's sort of like a dozen. If you say I have a dozen eggs, you have 12 eggs. If I have a dozen cars, I have 12 cars. It's basically the same thing, except a mole is many orders of magnitude more than a dozen. Well, a dozen is 1.2 by 10 to the power of 1. Avogadro's number is roughly 6 times 10 to the power of 23. So it's a really big number, but if you're talking about the number of atoms or molecules in a substance, then you would expect it to be a very big number. But of course, atoms weigh different amounts, and certainly molecules weigh different amounts. So 1 mole of hydrogen will be much lighter than 1 mole of iron, because a single iron atom is much heavier than a single hydrogen atom. And then that will be compounded and become even further, and have an even larger disparity when we're talking about different sized molecules, because molecules can get very large. That might actually strike you as somewhat of an odd claim, that basically if you give a chemist some, well, relatively small, a gram, 10 grams, whatever, some amount of some substance whose chemical formula is known, they can tell you to within substantial degree of accuracy how many atoms or how many particles are in that substance, and even though the number we're talking about is ginormous, like trillions of trillions, literally. So how on earth can they do that? Now, it's actually quite simple, because we can measure the mass of a single atom or single molecules, and of course the mass of different types of atoms, using relatively simple physical experiments. Basically, you apply a known, there are different methods, but one way is applying a known electrical force to the atom, to a charged version of the atom, and seeing how much it's deflected by that known force. The more massive the atom or molecule is, the less it will be deflected by a given sized force, and so you can calculate the mass to a relatively accurate degree. So if we know the mass of a single atom or single molecule of the substances, say it's water, and we've worked out the mass of a single water molecule, then all we need to do is weigh the sample of water that we have and divide that by the weight of a single water molecule, and we've got the number of water molecules that are in the substance. And you can do that for salt, you can do that for iron ore, you can do that for anything that has a known chemical structure, and the known chemical structure, which means you know the chemical formula of the thing it's made up of, and you also know the atomic weight of all the atoms in that chemical formula, which we do. We know the chemical weight of basically all the atoms. So that's a very useful concept, and we can apply that further as well. So for example, suppose that we have A and B, which react in a 2-to-1 ratio. So we need 2 A's for every B, and they produce C. Whatever those are, it doesn't matter. But we might not actually have an exact 2-to-1 ratio in the products of A and B. We might have slightly more A or slightly more B, or substantially more A and B. And so if what we can do is we can weigh the amount of the products that we have, the reactants that we have, then work out how many moles of each of them that we have, and then work out which of the 2 reactants, or 3, however many reactants you have, is the limiting reactor, or the limiting factor, which basically means the one that's going to run out first as the reaction proceeds. So for example, if you require a 2-to-1 ratio, but you have slightly fewer of the, if you have only 1.7 of A for every B that you have, then A will be the limiting factor. But if you have 2.2 A for every B, that means you've got slightly more than the 2-to-1 ratio of A that you need, so B will be the limiting factor. You haven't got quite enough of B relative to A to react everything, to react all of your reactants. So whichever one is the limiting reactor, the limiting factor, you can work that out by just weighing the substances you have, or the amount of them you have, and dividing that by the weight, or the atomic molecular weight of each of the atoms or molecules, working out the amount in terms of moles of each of the reactants you have, working out the ratio of those moles, working out and then comparing that to the ratio you need for a certain reaction to happen, and then work out which of the 2 reactants will be the limiting factor, and then using that knowledge you can work out exactly how much of the product will be produced in terms of moles, and then you can just multiply that by the weight or the molecular mass of each of those compounds or molecules that are being produced, and work out the total mass of the product that will be produced by the chemical reaction. And so that might sound complicated, but it's basically just an idea of using knowledge of moles and molecular and atomic masses, plus the chemical equations that you have, which tell you the ratio of atoms and molecules in the reactants and products, and plugging those numbers in and fiddling around with them to find out the information you want. And that could be how much product will I get for this amount of reactants, or how much of the reactant will I get, or what will the reactant weigh, or whatever. One final note on the concept of the mole. Remember, mole, it just refers to an amount of substance, so think of it like a big dozen, basically. You might hear of a concept of molar or molarity, which is used in reference to solutions. Molarity refers to the number of moles of solute per liter of solution. So solute is just something that's dissolved in a solution. So if you have a small amount of, say, salt, for example, that can be a solute. If you dissolve salt in a solution, but you only dissolve a small amount in it, that will have a low molarity, or low M is the abbreviation for it. But if you dissolve more and more salt in it, you'll get more solute per liter of solution, and therefore a higher molarity. And that may sound a bit sort of arcane, but it's just a word or concept that comes up every now and then. So if you hear it's 20 molar or 5 molar or whatever, or it has a high molarity, the bigger the molar or molarity, the more concentrated the solution is, basically, or the more solute there is. It's particularly often used for acids and bases. The higher the molarity of the acid or base, the stronger it is in the solution, the more of it is dissolved in the solution relative to the volume of the solution. Okay, so that's enough on stoichiometry. Now let's talk about thermochemistry, which only sounds slightly less scary, perhaps. Thermochemistry, though, is simply the study of energy and heat associated with chemical reactions, and also physical transformations, but we're going to focus on chemical reactions here. There are two basic types of chemical reactions in regards to thermochemistry. They are endothermic reactions and exothermic reactions. Endothermic reactions absorb heat, exothermic reactions release heat or emit heat. And Laplace's law says that the energy change accompanying any chemical transformation is equal and opposite to the energy change accompanying the reverse process. And there's also Hess's law, which says that the energy change accompanying any transformation is the same regardless of how many steps the process takes or what route it goes through in terms of chemical reactions. So those two laws basically just mean that whether an action is endothermic or exothermic, or how endo and exothermic a reaction is, doesn't depend upon which way it's going in, whether it's reacting forwards or backwards a sense, and it also does not depend upon how the reaction occurs or how many steps it goes in. It's just the total start and end process that matters for exo and endothermic, and for measuring transfers and energy transfers as well. Now, why are some reactions endothermic and some exothermic? Well, to understand that, we have to harken back to the definition of a chemical reaction, which is breaking some bonds and then reforming other bonds and shuffling atoms around in the process. Basically, you think of a chemical reaction as involving an energy hill. And this energy hill represents the energy level. Fundamentally, it's related to the energy level of the electrons that are surrounding the nuclei in the different atoms in the various molecules that are engaged in the reaction. So remember, the closer the electrons can get to the nucleus, the lower their potential energy is, because they're attracted to the positively charged nucleus, and therefore the lower the energy level is. So electrons will, in a sense, tend to reduce their energy level if they can. So sort of the total energy level of the electrons in all of the atoms in the reactants and the products can sort of be imagined as the overall energy level of the reactants and the products. And both of those, the energy level of the reactants and products, will be represented by sort of plateaus on either side of a central peak. Now, the energy levels of the products and reactants need not be equal to each other. They'll always be lower than the central peak, but one may be higher than the other, or they may be basically the same. If the energy level of the reactants is higher than that of the products, that means that after the chemical reaction, the products or the atoms have shifted around their electrons and shifted around their bonding relationships in such a way that they have lower potential energy. And because energy can't be created or destroyed, that energy has to go somewhere, so it's released in the form of heat. And that's why the reaction is exothermic. So in an exothermic reaction, the initial plateau will be higher than the lower plateau. We'll talk about the energy peak in the middle later on, but basically you go from a high energy level to a low energy level. The energy is emitted in the form of heat, and so we have an exothermic reaction. Endothermic reaction is the exact opposite. The initial energy level of the of the reactants, will be lower than the energy level of the products, because and the difference then has to be made up by absorbing energy from somewhere, which then reduces the temperature of its surroundings. So it absorbs heat from the surroundings, being an endothermic reaction. So to explain this concept more fully, in particular the idea of this central energy peak, what does that mean and what's going on there, and also to go into more detail about exactly why chemical reactions occur and when they occur and when they don't occur, I'm going to start talking about a field called collision theory, which basically explains how chemical reactions occur and why they occur. So for chemical reactions to occur, the reactant particles, let's say there are two of them, there could be more, but two's a common thing, they have to collide with each other. So remember that particles, whether they're atoms or molecules, are in constant motion. They have kinetic energy, which is basically random. They're just jiggling and moving around in random directions. The state of matter will affect how much they jiggle and move around. So in a solid, the atoms, the molecules will be closely bonded to each other, so they don't move around too much, but they're still jiggling in place in a sense, sort of vibrating. In a liquid, they can slip and slide around each other more. In a gas, they're completely free and move around and bump into each other. So it's often easy to think about these things as if by imagining that the molecules or the particles are gaseous and they're completely free to move around, but the basic idea still works in solids and liquids too. Just a bit harder to visualize. So, but for a reaction to occur, the reactant particles have to collide with each other. They don't just have to collide with each other, they have to collide with each other with sufficient kinetic energy in order for a reaction to occur. And the level of kinetic energy that they need is called the activation energy. So if the kinetic energy is just the energy that an object has as a result of its motion, if you recall, and so the faster that an object is, or in this case, the faster that the particle is moving, and also the more massive the particle is, the more kinetic energy it has. In the case of kinetic energy, velocity of the particle is more important. So the most important thing in terms, and also the mass of the particles doesn't change, but the velocity can. They're jiggling around randomly, so sometimes they're moving fast, sometimes they're not. So the total level of energy that we have in this collision is basically dependent upon the kinetic energies of the two particles that are colliding together. And if that combined kinetic energy or combined energy is sufficient to surpass the activation energy, then a chemical reaction will occur. Otherwise, it won't occur, and they'll just bounce off each other, and the particles will go their separate ways. Now, remember, the particles are moving about essentially randomly, so whether or not they have sufficient kinetic energy to reach activation energy is going to be random. But obviously, the lower that activation energy is, the more likely a given collision will have sufficient energy to reach the activation energy. So remember, the kinetic energy of a given collision is random, but it will have some distribution. And so the lower the activation energy is, the larger portion of collisions will surpass activation energy, and therefore the more often chemical reactions will occur between those two particles. So this activation energy represents the hill. Remember, we talked about the energy levels of the reactants and the products being plateaus on either side of a central peak. Well, this central peak or hill represents the activation energy, and what it means sort of physically is that in order for atoms to be rearranged and new chemical bonds to form, that is, in order for a chemical reaction to take place, we have to break apart the old bonds, or at least move them around substantially. And breaking chemical bonds, even breaking weak bonds, but breaking any kind of bond, requires energy to do. It's because essentially what we're doing is pulling those electrons further away from their nuclei, and that requires potential energy. It's kind of like picking an object off the ground. You're pulling it out of its gravitational well, so it requires effort to do that. Whereas if you drop it to the ground, it doesn't require any effort to do that. In fact, it expends energy and gaining kinetic energy as it falls. So in order to break these bonds, we have to pull the electrons out of their potential wells that they've fallen into. Essentially, they've fallen close to the nucleus. You have to pull them further back in order to break the bonds between the products, before we can then rearrange the atoms and make new bonds in the products. Now, the process, as I said, of breaking apart the initial bonds requires energy, and that energy is represented by the central peak. Basically, you have to increase the potential energy of the particles before you can reduce it again by forming the new bonds. And the amount of energy that you need to break apart the initial bonds is the activation energy, and it is provided by the kinetic energy of the particles as they collide with each other. Now, this concept of activation energy is separate from the concept of whether a reaction is exothermic and endothermic. So don't get confused. Endothermic and exothermic reactions both have an activation energy, and they both require they both have this central energy peak, and they both require this energy to pull apart the initial bonds. The difference is that in an endothermic reaction, the final energy level that you get to in the end, so the energy level of the products, is higher than that of the reactants. It'll still be lower than the central peak, but it'll be higher than the reactants, whereas in an exothermic reaction it'll be lower than the reactants. So basically, for a chemical reaction to occur, we just need the reactants to hit each other with enough speed, basically, and if they do, we'll reach the activation energy, and the particles will rearrange themselves, form new bonds in such a way that the reaction occurs. It's obviously a lot more complicated than that in terms of the details. One in particular, particularly for more complicated reactions and asymmetric molecules, the particular orientation with which the particles collide can affect how often or how likely it is for the reaction to occur. So if this particular bond over here on this hydrogen atom or on this oxygen atom or whatever has to break in order for the reaction to occur, then we need the other particle to collide with that, say, hydrogen atom, in order to strain and eventually break the bond, which is necessary to happen before we can then reform the bonds. If you break this other bond over here to this nitrogen, which we don't need to be broken, well, that doesn't help. So it depends upon the orientation and exactly where they collide, particularly with more complicated molecules, and so reactions get more complicated. Then, now this leads us to a discussion of reaction rates, because collision theory tells us that reactions occur when you when a collision occurs between two reactant particles of sufficient kinetic energy to exceed the activation energy. But there are things that we can do, a sense, or conditions that we can vary that will affect how often that occurs, how often we exceed the activation energy. In particular, the higher the temperature of the reactants, then in most cases, the more rapidly the reaction will occur, because temperature is just directly related to the kinetic energy of the substance. So if we have a high temperature, it means we have a high kinetic energy, which means the molecules or atoms are moving around at a high velocity. And so when they collide with each other, you also tend to have a high velocity. Basically, you're shifting up the distribution. There's still a stochastic distribution of velocity. So some particles are traveling slow, some are traveling really fast, most are traveling somewhere in the middle. But if you increase the temperature of the substance, then the overall average level, or the overall distribution, shifts upwards, and so the average collision is going to have more kinetic energy than it did before. And therefore, a larger portion of collisions are going to exceed the activation energy, and therefore the reaction will occur more rapidly. Increasing the concentration of one or more of the reactants will also increase the rate of the reaction, because basically you've got more particles in a smaller space, and so they're going to collide with each other more often, therefore producing more collisions, and therefore increasing the rate of the reaction. Now, something that I've mentioned before, but I'll talk about now because it's relevant to this reaction rates, is the concept of a catalyst. As you remember, a catalyst is just a substance or a chemical or some thing that accelerates a chemical reaction without being involved in the chemical reaction. So that means a catalyst does not appear in either the products or the reactants. It doesn't appear on either side of that chemical reaction. Well, you can put it there, but it will remain unchanged by the chemical reaction. So generally, we don't put it there unless we're trying to emphasize that it's doing something important. So the way that catalysts are able to accelerate chemical reactions is basically by providing an alternative pathway to get from the reactants to products that has a lower activation energy. So remember that central peak that we talked about? You have to pull the bonds apart before we can reform them again, or form the new bonds. That's a simplification, because there's not necessarily only a single way of doing that. There may be multiple ways of pulling the bonds apart, and some of those may require more pulling, in a sense, or in other words, have a larger energy peak than other ways of doing it. And if a catalyst can physically rearrange the products so that they can then combine in a way that produces that has a lower activation energy, then the catalysts, in doing so, will speed up the reaction, because by lowering the activation energy, a larger proportion of the collisions that occur will exceed that activation energy, and therefore the reaction will occur more rapidly. Catalysts are extremely important in biology, because living creatures are basically based on chemical reactions, and in particular metabolism, which keeps organisms alive, is just a bunch of chemical reactions. And in order for those chemical reactions to occur sufficiently rapidly for the organism to stay alive, you have to have catalysts. And so a lot of proteins that we make, for example, function as enzymes, which are just catalysts, speeding up chemical reactions. Otherwise, it would take you like a year to digest a single meal, which obviously wouldn't work so well. So we need enzymes to help us speed up those reactions. Okay, moving on to a slightly different topic, that of reversible reactions and dynamic equilibria. I won't spend too long on this. Basically, I just want to emphasize the fact that a chemical reaction often, in many cases, is not a simple linear process. If we have the reactants, there's an arrow, they combine with each other to produce the products, and that's it. A lot of the time, the reaction can actually go in both directions. So the reactants can be the products, and the products can be the reactants. So a good example of this would be the dissociation of hydrogen ions in water. So when we have water, we generally think that it's H2O, and we've just got a bunch of H2O molecules, but it's actually more complicated than that, because a certain percentage of water molecules are constantly breaking up into hydroxide ions, which is an OH, and then hydrogen ions, and then existing in that for a while, and then reforming later into a water molecule. And so the reaction goes in both directions. Essentially, we've got H2O produces OH negative plus H positive, but then you can also have OH negative plus H positive produces H2O. So the reaction works in both ways. And so the way we represent that is we have a double arrow pointing in both directions in the middle of that chemical equation. But each reaction doesn't necessarily happen as easily as the other one. So it might be easier to go from one way to the other way, or one direction might have a lower activation energy than the other, particularly if obviously one direction will be endothermic, the other will be exothermic, so there's going to be differences there. Basically, what will happen is that these two reactions will both occur at the same time, but one of them will happen more rapidly than the other. And so eventually we'll reach what's called a dynamic equilibrium, whereby the two reactions are still occurring, but they're occurring at the same the absolute number of each of the two reactions is the same, and so the relative proportions of the products and reactants are not changing anymore. So you can think about it. If I have, if it's my job to keep the shelves in a supermarket stacked with food, but there's also a constant rate of withdrawal of that food from the shelves by people purchasing it, then if you look at the rate at which the food is removed and the rate at which I replace it and compare those two, you'll eventually reach an equilibrium. So for example, if each product on the shelves has a 1 in 10 chance of being removed in an hour, but I can only replace 60 products in an hour, then if there are lots of products on the shelves, 1 in 10 of them is going to be removed every hour. So the total amount going out every hour is going to be large. The amount I'm bringing in is only 60, so it may not keep up, and we'll have a reduction in the amount of stock on the shelves. But as the amount of stock reduces, eventually 10% of that will be less than 60. And so if that occurred, there was hardly any stock, and say only 6 were being removed in an hour, then I'd actually be increasing the total amount of stock on the shelves because I'm bringing in 60 new items of stock an hour. We will reach an equilibrium of the amount of stock on the shelves when the amount I'm bringing in every hour is exactly equal to the amount that are being removed every hour. So it's not that there's none coming in or none going out, it's just that the amounts are the same, and so we reach what's called a dynamic equilibrium. It's like balance. The amount coming in is the same as the amount going out. And it's the same as in a chemical reaction. If one reaction is faster than another, then you'll tend to have the reaction going preferentially in one direction. So say we've got A going to B and B going to A, but A going to B happens much more than the reverse. So eventually we'll get almost all of the A's will convert into B's. And so even though the rate of B's going back to A's is very small, there are so many more B's than A's that the total number of B's to A's is the same as the number of A's to B's. And that will be our dynamic equilibrium. So if the rate of A going to B was exactly the same as the rate of B going to A, then the dynamic equilibrium would be 50-50 A's to B's. But if the rate of A to B was much, much higher than the rate of B to A, then in the equilibrium we'll have a very small amount of A and lots of B, because the rate of B going to A is so slow that you require a much larger stock of B in order to keep the directions being equal. And so then this sort of comes back to stoichiometry, where we look at what's called the equilibrium constant of a reaction K, which represents the rate at which the two reactions occur, and then we compare how much of the stuff we have and then work out what the equilibrium quantities and masses of the reactants and products will be, and therefore we can work out what's going to happen. Changing the temperature always shifts the dynamic equilibrium towards more of some products and less of something else, but the direction will basically depend upon which reaction is favored there. Interestingly, the presence of a catalyst does not change the dynamic equilibrium or the concentrations and equilibrium of the reactants and products. So changing temperature does, but a catalyst does not, and that's because basically a catalyst will, most of them at least, speed up the forward and reverse reactions to the same degree. So it'll reach equilibrium more quickly, but the ratios will be unchanged. Okay, so that's reaction rates and reversible reactions. One final thing that I would want to do before closing is just take a quick look at the different types of chemical reactions. Now, remember I talked about exothermic and endothermic reactions, but that's just the two types in thermochemistry. The types of reactions in terms of what's actually happening, well, there's a number of ways of categorizing them. In particular, we can have synthesis and decomposition reactions. They're probably the two simplest types. In a synthesis reaction, we've got two or more simple substances combining to create a more complex substance. So basically that's A plus B equals C, or produces C. So for example, hydrogen gas can react with oxygen gas to produce water. Decomposition reaction is the exact opposite of a synthesis reaction. We have a complex substance breaking down into simpler components. So for example, you run an electric current through water, you'll break it up into oxygen and hydrogen gases. We also have two types of displacement reactions, single and double displacement. Basically, in a single displacement, we have a compound and another element that's reacting with it. We remove one element from the compound and replace it with the other element it was reacting with. So basically, think of it as like this. We have AB bonded together, we add C to it, and that produces AC bonded together, and now B is separate. Or it could be A going out and B staying in, whatever. That's a single displacement. In a double displacement, we basically have two compounds which swap ions with each other, or which swap elements with each other. So for example, we could start out with sodium chloride and silver nitrate, and then form sodium nitrate and silver chloride. So the sodium and silver just swap their partners in that. So that the form of that would be AB plus CD produces AC plus BD. Those are very general categories, just describing exactly what's moving around. Where more specific categories of chemical reactions that you'll come across are redox reactions, or oxidation and reduction reactions. Those involve the transfer of electrons, and they're associated with batteries. One particular subset of redox reactions are combustion, which is when something burns. So that's involved in explosions and fires and so on. So Oxidation reductions are very important types of reactions. Another type is acid-base reactions, which is a specific type of a double displacement reaction where you have an acid and a base and basically they swap hydrogen atoms. They can also be important in batteries, but they occur in many different industrial processes and other things. So, and acids and bases, I think you hear about a lot. So, in future podcasts, I'll devote one specifically to redox reactions and another one to acid-base reactions. There's also precipitation reactions where a solid forms in a solution of something else. So, if you mix salt or mix sugar in your water and then it precipitates out after a while into crystalline sugar in a solid form, then that's a precipitation reaction. And there are many others too, but those are some of the basic ones. Anyway, that's about all I wanted to cover in this introductory podcast. I hope it was reasonably clear. If you enjoyed this podcast, please spread the word and share it with more people. I'm always looking for more listeners. More reviews on iTunes or some other aggregator site would also be much appreciated. Last time I checked, I had 2 reviews on iTunes. I'd like to have enough so that I could actually get one of those star ratings on iTunes. That would be good. I don't know how many ratings I'll need for that to occur, but your 1 rating would help with that. Please visit my website at fods12.podbean.com, where you can download old episodes and comment if you want. My email address is fods12@gmail.com if you'd like to make a comment or a suggestion about something you'd like me to cover. Thanks for listening, and I'll talk to you next time.